Okay, so so last time we actually went in deep into the chapter of alkenes, right? And so last time we reviewed and learned some concepts related to the reaction diagram, which is the very foundation for all the reactions you are going to learn in the next chapters and all the chapters remaining. Okay. For example, you need to be aware of the concepts of intermediate and transition states, and for example, rate determining step, things like that. Okay, and we started the electrophilic addition of hydrogen halide, like hydrogen bromide, hydrogen chloride. Okay, and I introduced the Markov-Nikov's rule, and in the very foundation of that rule is the stability of carbocations. And in order to explain the Markov-Nikov's rule in the addition of HX, so you also need to understand the Hammond postulate. All right. There are some old things you need to do and keep in mind. So the stereochemistry drill is still open until after the midterm 1. So if you have any question regarding that drill, you can come to my office hours on Friday, and you can also send me an email or send an email to the tutor. So hope we can solve that problem for you. And the tutorial session starts tomorrow, and the tutor will explain will prepare some questions and problems that is very close to the problems you are going to solve in the midterm and exams. Okay, and the midterm 1 is I think it's 3 weeks away. All right. So at the end of the last time, so this concept, this carbocation-like transition state is really important in explaining the Markov-Nikov's rule. And I will just do a brief review of that. And so why the addition of HX follows the Markov-Nikov's rule is not because the Markov-Nikov's rule goes through a more stable carbocation intermediate, not directly, but because the carbocation transition state it goes through is also lower in energy, and the transition state looks like the carbocation because the Hammond postulate, and because the energy between the transition state and the product are very close, and the product is carbocation, so the transition state looks like carbocation. All right, so that is a brief like a chain of logics for you to explain the Markov-Nikov's rule. All right, so we have a more stable carbocation, and because the Hammond postulate and the transition state resembles carbocation because the energy are close, and so we have a more stable transition state. And because of the more stable transition state, so the Markov-Nikov pathway has a lower activation energy, and because the step 1 of generating the carbocation is the rate determining, that means the overall electrophilic addition is faster following Markov-Nikov's pathway, and which eventually gives the Markov-Nikov's product. And this is an explanation we go through. So the red one is the Markov-Nikov's pathway, and it does generate a more stable carbocation, but what we care about is the transition states, relative stabilities, which because the transition states looks like the carbocation, so because the tertiary carbocation is more stable, so its a carbocation-like transition state is also more stable. So it's much easier for the reaction to follow this lower activation energy pathway to eventually give the Markov-Nikov's product. Okay, and we also talk about, because we already learned that primary carbocation is less stable than secondary, and secondary is less stable than tertiary carbocation. So there is an order of stability between carbocations. 1 is less stable than 2, 2 is less stable than 3. So for a reaction, if you want to judge whether for the reaction, if the difference in transition state energy is higher, like the 1 versus 3, then the lower transition state energy difference, like 2 versus 3, then we can predict that the Markov-Nikov selectivity of this first reaction should be larger than the second reaction because the energy difference is larger. So in the first reaction, you can see this Markov-Nikov product is the only product which means the anti-Markovnikov product is not generated at all, at very high selectivity, right? But in the second one, because the energy difference between the transition states compared with the first reaction is lower, so that means that the selectivity is also lower. That means that although the major product is still Markovnikov, the other one is generated, but in a very small amount. So you can clearly see that the selectivity of the first reaction is much higher than the second reaction. Okay, then let's talk about something new here. So we talked about the residual selectivity or residual chemistry of the HX addition, which is following Markov-Nikov's rule, right? So how about stereochemistry? So if you still remember the definition of the stereochemistry, it means that if it generates two products with the same bond connection, you can see methyl is still here, methyl is still here, but it has a different 3D orientation, like the relatively cis-trans relationship between all these substituents. So let's see what stereochemistry the HX addition have. Okay, so as alkenes have two phases. Okay, so what we care about is that the H and the chloride add to the same or opposite phase. Okay, so so the conclusion after we investigated so many reactions is that, so if H added to the top phase, like generate a carbocation, right? And because the carbocation look like here, it's flat, all right? So it is these three bonds are flat. And then the chloride can either attack from the above or from the bottom, okay? So let's say if the chloride attack from the above, the same side of the CH3, then what we generate? So the product we have should be look like the two methyl group is on the different side. So if we have the chloride, the methyl is the same side, like the chloride and the methyl here are cis, both pointing to you, right? And what if the chloride add from the bottom? And then the chloride will have a trans relationship with the CH3 on the other carbon, right? Just like this product. So this chloride pointing down away from you, and the methyl on the other carbon is pointing towards you, all right? So the conclusion of that is HX addition is not stereoselective. So it does not generate one stereoisomer predominantly. So both of these products will be generated. And for a more detailed illustration of this addition, you can see this form. All right. So if the H add from above, okay, the H is pointing to you, right? And this carbocation is flat. So chloride can either add from above to generate it here, or up below the plane to get here. So if the first H addition is below the plane, you can see the H is pointing away from you. And then the flat structure also have two pathways. One is the chloride pointing to you, the other is chloride pointing away from you. All right. If you look at these four structures from a single starting material, you can try to figure out what's the relationship between them. So if you look at the first one and the fourth one, okay, what's the relationship between them? So it's enantiomer, all right? And then the second one and third one, they are also enantiomers. But for the second one with the first one and fourth one, they are diastereomers, okay? So all four products will be generated, and there are two pairs of enantiomers. So both syn and anti addition occurs to form cis and trans isomers. So thus, this reaction is not stereoselective. Okay. So we really focused a lot on the carbocation and its implication in the selectivity of the electrophilic addition. So, but how do we know the carbocations are really the intermediates of this reaction? So first, we want to make sure that the carbocations are a real intermediate that the reactions go through, right? So as early as like 1901, people already discovered the presence of carbocation. For example, if you have this colorless compound, which has trimethyl triphenyl methanol. Okay, so in the presence of an acid, this OH can leave, all right, to generate a yellow stuff. And people found out the yellow stuff is actually a carbocation. Another characteristic property of carbocation is that some carbocations can rearrange. Okay, so you can start from one type of carbocation and rearrange to another carbocation. And the driving force of this rearrangement is usually the product. The resulting carbocation is more stable than the starting carbocation. Okay, if you see the rearrangement, a typical rearrangement is listed here. So you have a primary carbocation, which the carbocation is listed here, has 2H and carbon. Okay, it can go through a rearrangement to form this tertiary carbocation. And as you know, the tertiary carbocation is much more stable because of more substituents, right? So how did that happen? So for this primary to tertiary carbocation rearrangement to happen, it goes through a process called a 1,2 hydride shift. And you may wonder what is a hydride. You already know the concept of proton, right? Because this is just H without any electrons. It's a H plus, right? So you also probably know the H radical, which the H has only one electron. So that means it's a radical. Okay, this is a typo. I need to check that. And for the hydride, it means the H has 2 electrons. Okay, so this hydride shift is that this pair of electron goes with the H. So if this has one pair of electrons and neutralize this one, and because the bond's electron goes with the H, the carbon now is positive. Okay, so the H atom is not happy with this arrangement, and it bring the 2 electrons it shared with the carbon together with him and move to another carbon, so that this unstable carbocation now becomes a more stable carbocation. All right, so the effects of carbocation rearrangement is significant in the electrophilic addition. So let's look at this result. So if you have this type of alkene and it react with a hydrochloric acid, okay? So this product, so the H added to 2H, the chloride added to 1H. So that's following Markov-Nikov's rule. So this is the standard Markov-Nikov product, okay? But what people observed is that the chloride, and there is another product, that the chloride is not on the middle carbon, but on the more crowded carbon here, right? So how do you explain this result? Because that is not the Markov-Nikov product, nor, so this is also not the anti-Markov-Nikov product. So how does that happen? So how does that happen is that, so for example, we have, I marked this hydrogen green on this carbon, okay? So the first step, as we learned, that the alkene will add into the hydrogen, the proton, to generate a secondary carbocation, right? And the secondary carbocation, once it recombined, once the chloride attack this carbocation, will generate the Markov-Nikov product. But as we just learned, that this secondary carbocation has a trend to rearrange to a tertiary carbocation, which is more stable. So this hydride, the green hydride, will move or migrate 1,2 rearrangement to this carbocation. And then now it becomes the tertiary carbocation. So once the tertiary carbocation is generated and it is more stable, the chloride can now attack the tertiary carbocation and to have this product, which what we call is the rearranged addition product. So it's not Markov-Nikov, it's not anti-Markov-Nikov, but it's a rearranged product because of the rearrangement of the carbocation. All right. So if in the exam I listed these 2 starting material and asked you to write down what's the product of these reactions, I know it is very hard for you to predict how fast the rearrangement, so which is bigger, which product is a smaller amount, right? So I'm asking you to assume both products will be formed. Okay, so if I ask you, if I give you these 2 starting material, and also it will generate a carbocation that has the probability to rearrange, then you need to write both of the product, the Markov-Nikov product and the rearranged product. Okay, so not only will the hydride do the 1,2 shift reactions, so even an alkyl group can do the 1,2 shift to rearrange to a more stable carbocation. For example, if you have this primary carbocation linked to a terbutyl group, which has a carbon linked to 3 methyl groups. All right. So because this is a very unstable primary carbocation, now because the carbon does not have any hydride, so the methyl will migrate. So if the methyl migrates with a pair of electrons to neutralize here, a more stable tertiary carbocation will be generated. So if you look at these ring structures, again, you have a primary carbocation, and in order for it to migrate to generate a more stable carbocation, this alkyl group will migrate to give this secondary carbocation. Okay, so this actually, so some of you may wonder, oh, why doesn't the hydride migrate to generate a tertiary carbocation here, right? So this is beyond the requirement of this course, and this has to do something with that the tertiary carbocation with this strained ring is not that stable. But you just need I just want to let you know that the ring enlargement reaction can happen with those 4 membrane to 5 membrane, but this will will definitely not be on the exam to let you judge. So which will migrate, okay? So but this one, because the carbon only has 3 methyl groups, so only the methyl can rearrange. All right. So this one you just need to be aware of that. All right. And so there are some conclusions here. All right. Alkyl shifts occurred by moving the electron pair with the group. So the methyl moves with a pair of electrons of the bond here. So the carbon becomes positive. Okay. And the second one is that primary carbocations, they are all so unstable, so they always undergo rearrangement. So, so for the alkyl 1,2 alkyl shift, there are also some phenomena we observed. Okay, so for example, so this is similar to the substrate I draw, but instead here are the carbon with 3 methyl groups instead of 2 methyl and 1 hydrogen. Okay, this methyl group I marked in green. So it will react with HCl, generate carbocation. If it recombine with chloride at this stage, you will have the Markov-Nikov product. But if the methyl migrate, the carbocation is generated at the more stable position, which is a tertiary carbocation. And the recombination of chloride at this stage will give this rearranged addition product. All right. So again, if you see this kind of problems appearing on the midterm or the final exam, so you should assume that both products will be formed. All right. So you need to write down the Markov-Nikov product and the rearranged product. Okay. So, so as we said, so carbocation rearrangements are driven by achieving more stabilities, and that also means if the resulting carbocation has the similar stability as the starting carbocation, so the rearrangement probably won't happen. Okay, so look at this alkene. If it add to HBr, so the carbocation is generated at this secondary position. All right, and then you may say, oh, is it possible to rearrange? So what if it is rearranged? Let's say if you have a carbon here, okay, and if the hydride rearranged to this carbon, so the resulting carbocation, okay, is still a secondary carbocation. All right, since the starting material is a secondary carbocation, the resulting material is also a secondary carbocation. So we say so the rearrangement doesn't give the carbocation more stability. So that means it probably won't happen. It won't happen, okay, if the carbocation does not become more stable. So so the product of this addition is, as usual, the Markov-Nikov product, and no rearrangement product is appearing here. Okay, so So if you encounter this kind of problem in midterm or final exam, and you see if it rearranged, the stability doesn't change because if it's both secondary carbocation, you only need to write down the Markov-Nikov product. Okay, that's 100% correct. All right, I think this is the part 1 of the chapter 5 and 6, and we will start part 2. So we just covered the electrophilic addition of HX to alkenes to generate alkyl halide. So we are going to start to learn something relatively easy and comparable to the alkyl halide generation, which is the generation of 1,2-dihalide from alkene. Okay, so instead of adding HX to the double bond, we now add XX to the double bond. All right, so this is the easiest halogen addition to alkenes. You have ethylene and you have chlorine, and well, one chloride add to this carbon, another one add to here. So you have a 1,2-dichloroethane. All right, so we know that bromine and chlorine add to alkenes to give 1,2-dihalides, and this is a very important process in industry. Okay, generating a lot of basic chemicals that is important for a lot of industries, but people do not use F2 for the dihalide addition because F2 is very reactive and also very dangerous chemicals. So how about I2, the iodine? So iodine addition is possible, but it's thermodynamically unfavorable. What does that mean? So the alkenes, it does add with the iodine to generate this product, but this product itself is too unstable. It's very unstable with for 2 iodine on the neighboring carbons. So actually, if you have this compound will revert back. It will eliminate back into the alkene and the iodine. Okay, you can see the equilibrium arrow here. So the reaction favors start material. So this is never a very practical way to make diiodine because the product is so unstable. The reaction barely proceeds. All right. So most of the addition of halogens we deal with is with bromine and with chlorine. All right. So the mechanism seems simple, and it's similar to HX addition, but there are a major difference. Okay. For example, in the HX addition, so it adding to the H first to generate a carbocation, right? And then you have, just as we talked like several minutes ago, you have the cis product and trans product because the HX addition is not stereoselective. The bromide can add from the above or it can add from the bottom. Okay, so if the bromine Br2 addition goes through the similar pathway, so let's say the first Br at here, if the second Br addition can happen at the above or the below, it can also give cis and trans product, right? But but that is not the case. Why? Because because if it goes through a similar mechanism as the HX addition, it will predict both syn and anti addition product. But in the reality, when this cyclopentene reacts with bromine, we only observe trans 1,2-dibromo cyclopentene here. So the experiment's result shows us that it might not go through the similar mechanism, might not go through the same mechanism as the HX addition, because we didn't observe trans and the cis product. Only the trans product is observed. So in this case, we must come out of a modified mechanism to explain this stereochemistry outcome, right? Because the exclusively anti-addition result. So first, you need to memorize if you can understand the mechanism so well. So all the additions of halogens, it exclusively gives anti-addition. Okay, so for the Br2, so one Br is pointing to you, one Br is pointing to the back of the paper. So for the chlorine, the same, one chloro up, one chloro down. Okay, so the reason behind this kind of exclusive anti-addition is that the intermediate formed from the addition of alkene to bromide, bromine is a cyclic brominium ion. So it's not an acyclic carbocation. Okay, so you need to be very clear about this structure. So the alkene react with this bromine, not generate a carbocation, but generate a three-member ring with the positive charge on the bromine. Okay, how does that happen? So if it adds into HBr, so the H is here, you have a planar carbocation, right? The bromide can above, bottom, attack. Okay, so what we found out is that when it reacts with bromine, once the carbocation is generated, so the bromine actually can interact with this carbocation, because in the H, you only have 2 electrons, and the 2 electrons are bonded with this carbon. Okay, it's not free electrons. Okay, but for the bromine, it has 3 electrons that is not bonded, 3 pairs of electrons that's not bonded, and you have very electron deficient species, and you have so many electrons. So what it does is that the bromine wants to share its electron, like spreading its electron density with the carbocation. So everybody is happy, right? The electron deficient carbocation now gets some electrons, and the electron-rich bromide now shares some of its electrons. Very happy, okay? So as I said here, bromine having long pairs shares positive charge with the carbon. So the intermediate now look more like the 3-membrane, what we call the brominium cation. Okay, and because this is not a free carbocation, all right? So because this is a stabilized carbocation by the neighboring Br, so it does not rearrange because it's not a carbocation. So for the bromine addition, there is no carbocation rearrangement. So once this brominium ion is generated, then the Br now have only one choice to attack. Okay, because you can see the bromine is here, like in this graph. So it's very crowded on this side. Basically, the bromine blocked this side. So for the bromine anion here to attack and open this ion, it only can do the backside attack. Okay, that means attack from the opposite side of the brominium ion. Okay, it does not attack from here because it's so crowded. It only attacks from the back. Okay, when it's attacked from back to this carbon bromide bond break. All right, then you have the trans 1,2-dibromo product. Okay, so that is the origin of the anti-addition product. Okay, because the bromine cannot attack from the same side, and the backside addition will give the trans 1,2-dibromo product. Okay. Okay, so the exclusive anti-addition origin from the bromide attack from the open side, which is also the opposite side of brominium ion. Okay. So as we, if you still remember, we did some basic graphs of the HX addition, and you give the two pairs of enantiomers. Okay, we can also do the same same graph here, that the bromine addition can either happen at the bottom or at the above side, right? So if the bromide is generated at the bottom, the bromide anion attack from the top. So you get a trans product with the enantiomers to each other. So if the initial bromide addition happened at the top face, and the bottom face attack of the bromide anion also give a pair of enantiomers, also trans. Okay. And so what's the relationship between this one and this one? So they are the same, right? So you can see the difference between all the graphs here. So for the HX addition, because the second addition is not stereoselective, so you can generate 4 products, but there are diastereomers. So this one is diastereomers with these 2. But for the bromide addition, because the second addition is stereoselective and exclusively gives anti-products, so now you don't see any diastereomers because all of them are anti. Okay. So here is a brief practice. I want you to do it with me, which is that to write down the product, since now you know that the bromine addition is the anti-product exclusively, right? Then you should be able to write down these two products, okay? So let's do it one by one. All right. So if you have a cis alkene, like this one, these two methyls are on the same side of the alkene. All right. Then you add into bromine, you generate this kind of brominium ion. Okay. And the bromine now will attack from the bottom face of this alkene because it's because this top face is so crowded with the bromide occupying it. Then you have two sides to attack. One is that if you add to the left carbon, this bond will break. If you add from the right carbon, and this bond will break. Okay, if you add from the left one, the product is Br here. This bond break. This Br is up. Okay, this Br is up. Okay, this is 2s, 3s dibromobutane. And then if you go through the pathway B, which attack from the right carbon, and this bond breaks. Now this C-bromide bond will be up here, and the bromide will link from the bottom here. So this is 2R, 3R dibromobutane. Okay, so what's the relationship between two? They are enantiomers. You have 2S, 3S. You have 2R, 3R. So the addition of bromine to a cis alkene with two same groups will give a pair of enantiomers. Okay, so how about the trans alkene? So you have a trans alkene which has two methyl groups on the opposite side of the alkene. One is here, one is in the back. Okay, after you add to bromine, you generate a brominium ion. Again, you have two pathways, A and B. If you attack A, it will look like here. So this bond breaks, this bond still here, which is pointing up, this bromide pointing down. How about attack from B? So this bromide bond is still here, so pointing up, and this will bond it here, pointing down. Okay, so this is 2s3r, and this is 2r3s. So if you don't know the concept of methyl group, methyl compound, you would say they are enantiomer, but they are not enantiomer, okay? Because they are achiral. So if you rotate this bromide to here, let's say, and the H will be here, pointing to you, the CH3 pointing back. So there is a mirror here. So although this compound has two stereocenters, two carbons, okay? But it also has an internal plane of symmetry. So that already makes it achiral. So this is called a methyl compound, right? Still remember the concept, right? So if you don't remember the concept of methyl compound, you are very dangerous, okay? So you need to get familiar with all those concepts you have learned in the past weeks, okay? It's only 2 weeks until the midterm, okay? If you haven't know the methyl concept deep in your mind, you really need to hurry up, okay? So the stereochemical outcome of this trans alkene is that you generate a methyl compound, okay? And so cis gives a pair of enantiomer, and the trans gives an achiral compound, which is methyl. All right. So now we need to introduce you to a new concept called the stereospecific reactions. So these are the reactions that come to one isomers of the starting material, let's say cis, to one stereoisomeric product, okay, to a pair of enantiomer from cis, and convert another isomeric substrate, which is trans, to a different stereoisomeric product, which is a methyl, okay? So different isomers of the starting material gives different stereoisomer product, okay? So A to B, but its stereoisomer A prime gives to B prime. So we say the addition of halogen is stereospecific because of this result. So let's give a summary to compare these concepts we have learned so far. So regioselective reaction is that if start from the same product, you have a pair of constitutional isomers generated, and more of the B is formed than C. So one constitutional isomer predominates, okay? So we say it's a regioselective reaction. So if it generates two stereoisomers and one of them predominates, like B is more than C, then we say it's a stereoselective reaction. So we say a stereospecific reaction is a reaction that generates one isomer to one isomer. Okay, so A and A prime are stereoisomers, B and P prime are stereoisomers, and A only generates B. A prime, it generates B prime. So that's what we call a stereospecific reaction. Okay, so now it's a real practice with me. All right, so you have a product here, all right, and then if in the exam I ask you to write down the starting material, you should be able to, just look at the structure of the product and look at the condition of the product and tell me what's the starting material. All right, let me do this with you together. Okay, let's see here. So I'm going to show you if you see this problem on the exam. How do you solve this problem? Okay, think. So if you see this product, because you see, oh, the addition is a bromine addition, okay? So that means, and you should keep in mind that the bromine addition is anti-addition, right? Okay, so if you know this, then you see to really get the starting material, you need to, oh, my Apple Pencil doesn't work. Oh, that is bad. So this is an accident. So I cannot write on my iPad right now. So I'm going to write on the PowerPoint, see if I can really be good at writing it. Okay, let's see. Pointer option, pen. Okay. So if you see this product, then you need to make it look like an anti-addition product, right? So you probably need to write like this. So please don't mind my writing here. Okay, and then you have a phenyl group. We can abbreviate as phenyl, and then we have a hydrogen. Okay, then what should I do? Okay, and then what you need to do is that you need to rotate this double bond, this single bond. Okay, make it look like empty. So make this bromide in the bottom phase. Okay, so if you rotate this single bond to make the bromide at the bottom, okay, then you will also rotate these two sigma bond, right? And now the H used to be the back. After the rotation, it goes to the above, to the front. Okay, what it looks like will be, oh, okay, the hydrogen now looks like this. Okay. And how about the phenyl? The phenyl will be rotated to the back, okay? Okay, you have a phenyl. Sorry again for this ugly drawing. And now you have the quite anti-like product, right? And so that let's assume that the brominium ion will form here on the above, and the bromide attack from the bottom, right? So the original double bond will be here. So will be here, right? And then if you recover the bromine starting material, you will have an alkene, which has the phenyl in the back. This phenyl is also in the back, right? The hydrogen and this hydrogen will be in the front, okay? So what your starting material should like the phenyl, you have 4 bonds, all right? And the 2H will be in the front. And the 2-phenyl will be in the back. Okay, the pH means phenyl, which is this big structure here, all right? All right, so from this ugly drawing, we can see that the trick to solve this problem is that you need to make it look like an addition product. And you assume the bromine will be, bromine is from the brominium attack from this bromine. So this 3-membrane brominium ion is formed here. Okay, then you look at all these 4 groups orientation. Okay, then you have a 2 phenyl in the back. Then that means in the alkene, the 2 phenyl on the same side. All right, so again, if you see the product in the exam or midterm, you just, if you see the starting material, if you see the reagents used, you need to figure out what's the reaction, and you figure out what's the stereochemistry of this reaction, and then try to figure out the starting material. All right, okay, so that's the dibromine, that's the dihalogen addition. And let me charge my Apple Pencil. Okay, so the next reaction I'm going to talk with you is a little variation of the dihalogen addition. But in this case, what we call is halohydrin. It's a halohydrin formation. So you can see the condition is quite similar. You have the alkenes here, and you have a bromine and chlorine here. Okay, and then these used to be the major product, which is the dihalogen addition, right? With 2 bromide adding to the 2 carbons here, and 2 chloride adding the 2 carbons here, right? These 2. But now, the magic things about this is that if we use water as the solvent for these reactions, these 2 dihalogen addition now becomes the minor product, all right? So the major product now becomes bromohydrin and the chlorohydrin. Okay, so that's the reaction, what we call a halohydrin formation. And you see the change of solvent actually has a major impact on the reaction. Now the major product is not the dihalogen addition. So, and you can see this product as the formal addition of HOX into the alkenes, right? So the HO adding to this carbon, X adding to this carbon. So, but the actual region is not HOX, but it's the dihalogen and in water, or in water organic mixed solvent. So this is the key to achieve this halohydrin formation. Okay, so the mechanism of the halohydrin formation, the first part of mechanism is similar as the dihalogen addition. So the alkene will add into the bromine first and kick off this bromine to generate again the this brominium ion. And now, instead of the bromide adding to this carbon, the water adding to carbon. Because why? Because water is used as a solvent, and the solvent is in a very, very large amount. It's a more abundant nucleophiles. Okay, and the abundant nucleophile will add into this brominium ion instead of this stoichiometric amount of bromide anion. And once the H2O adding to here, okay, form this bond, and this bond breaks, and to give this hydronium ion. And this hydronium ion will be followed by a deprotonation step, which the abundant nucleophile, the H2O, will remove one of the proton from this ion to give this halohydrin formation reaction. Okay, so instead of a two-step reaction of the dihalogen addition, which is after the brominium ion is formed, followed by the attack of the anion, bromide anion. So the reaction now goes through 3 steps to give the halohydrin formation. And the second step is the attack by the water. And the third step is the removal of the proton from this addition product. Okay, so as it proceeds through similar reactions, and you really need to pay attention to the solvent in every reaction we write. So if we write organic non-nucleophilic solvent, it will give us a dihalogen formation, like the trans addition here. But if we use a nucleophilic solvent, like the water will participate in the reaction to intercept the dihalogen addition and give this halohydrin formation here. Okay, so it's the same mechanism with this other nucleophilic solvent like the ethanol. So if you use ethanol as solvent, so instead of water adding to brominium ion, and now the ethanol will add into the brominium ion. So instead of giving OH, then you give the OSO group here, okay? And because the OH act like the same way as the OH in the water, it will add into brominium ion to open the brominium ion to give this product, okay? So how about unsymmetric alkenes? All right, then so there is also some difference from the dihalogen addition and with this unsymmetric alkene. All right, so what we found out is that so the bromine will be on the less crowded side of the alkene, okay, and the bromine's relationship with the OH is trans because the brominium ion, right? But the bromine will be only on the less crowded side. And with the bromine on the more crowded side, these two products will not be formed. So there must be some mechanism to explain this kind of preference, okay? And what we say is halohydrin formation is a regioselective reaction, and because the bromine only goes to the less crowded side, and the CO bond will form at the more substituted carbon. So what happened? Okay, so what we found out is that with the unsymmetric alkene addition to bromine, and so it's not really an brominium ion that is symmetrical. So it's actually a brominium ion that resembles tertiary carbocation. Okay, so if you see an unsymmetric alkenes, and if it adds into bromide, it will generate something like a three-membrane brominium ion, but it's not exactly three-membrane. So it's not like this with the, it's not like this bond and this bond and same. No, okay? It's more like an intermediate between the three-membrane and the carbocation, all right? And because the carbocation has a stability preference, so the carbocation, the positive charge, the partial positive charge will be generated at this more crowded carbon, not like here, okay? Apparently this is less stable than this one because the positive charge want to be stabilized by all the substituents. Okay, now because there is a regioselective preference here, so now the water will attack at this carbon preference like selectively. So it's still backside attack, but it will not attack here. It will attack here because this intermediate looks like a carbocation. Okay, so once the H2O attacks here and another H2O remove a proton, it will generate the trans product, and it will generate a regioselective product, which the bromide is on the less crowded, and the CO bond is generated as the more crowded carbon. Okay, so the conclusion is that unsymmetrical brominium ion resembles tertiary carbocation. Thus, the reaction of unsymmetrical alkenes is regioselective, with the CO bond generated at the more crowded side. And the origin of this regioselectivity is because brominium ion, it looks like tertiary carbocation, and the positive charge is at the more crowded side, which will accept the attack from the nucleophile. Okay, so that's the mechanism of the halohydrin formation, especially a special case of the unsymmetric brominium ion. Okay, I think we will have there will be definitely this kind of problem in the midterm that if I give you the product and give you the regions, and you need to write on the product, write on the starting material. Okay, so I'm going to go like be serious about this and talk to you more about how to solve this problem logically. Okay, so if you see the product and you see the regions, okay, the first thing you want to figure out is what reaction. Okay, so what reaction is happening here? So, and it's very clear in this case because you have a bromine, right? And you have organic solvent, bromine, and you have a dibromide on the two carbons. So that means you have a dihalogen addition. Okay, so dihalogen, di-X addition. Then you need to figure out, you need to use your knowledge learned from the class. What's the stereochemistry? Stereochemistry of dihalogen addition. Okay, so if you still remember, then it's anti. Okay, anti. So then if you figure out, okay, it's anti addition of two bromine,
then if it's anti addition, so the bromide should be anti, right? And if I draw the molecule like this, it doesn't look like anti. Okay, so we need to rotate this bond to make this molecule look like anti. All right, so let's keep the left side. Hydrogen pointing to you, funnel pointing back. Oh, this might be too advanced for you. Okay, so let's just make it look like this. Okay, so if you rotated the sigma bond here to make the bromide in the bottom, right? And you need to know that this are the same plane. Okay, and then if you do so, so the bromide will be rotated into the back here, and the hydrogen will in the front here. So hydrogen here, and the funnel pointing back. Okay, now you have this. Okay, then you also need to know that for the dihalogen addition, they go through a brominium ion. Okay, so what kind of brominium ion can you imagine? So it's like, so look like there is a 3 membrane here, right? So this product comes from a brominium ion that can be drawn like here. Okay, then you can imagine the brominium ion, Br plus, all right? And the hydrogen in the front. And this hydrogen is also in the front. The funnel in the back. Also funnel in the back. Okay, so just to make sure you understand this, okay? So the bromide attack will from here to generate this one, right? Attack from here, this bond breaks, the bromide is here. Okay, so now you have a brominium ion intermediate, then it's very easy to figure out what's the alkene starting material, right? So the alkene starting material is like 2 funnel is on the same side, because in here, they are both pointing to the back, okay? So the product is very easy to draw now, is the 2 funnel on the same side. 2 hydrogen on the same side. Okay, so that's the correct answer for this problem. So you have, I gave you the product, I gave you the regions, and you give me the starting material. All right. Okay, that's much more comfortable using the pencil. Okay, and okay, let's go back to the slides. Okay, so after we talked about the halohydrogen formation, then we move on to another reaction of alkenes called hydration. Okay, hydration is can be viewed as the addition of a molecule of water into the alkene to give alcohol. Okay, so it's an addition of HOH that is called hydration. To be in a funny way, it's like the alkene is drinking. Okay, alkene is drinking, and to become alcohol. Wow, that is a very good joke. Okay, so the alkene is hydrating to give alcohol. All right, so it is then a very important industrial process. Basically, millions of tons of ethanol is generated in this way from easily available ethylenes. Okay, so unlike previous addition reactions, now the hydration of alkenes actually needs a catalyst, a strong acid catalyst. Okay, so we will talk about the catalyst later and the detailed mechanism. And for the regional selectivity and for unsymmetric alkenes, it's a Markov-Nikov addition. So I would say because it's the first addition of the alkene is to a proton, right? And it's like the HX addition. And if you remember, the HX addition is following strictly the Markov-Nikov's rule. So the same for the hydration because the first step is adding to the proton. Okay, so for this example, you can see the water added in this way with the H on mole H, Markov-Nichols major product, which is a major product, and the primary alcohol with the H added to the last H here, no H here. So that's anti-Markov-Nichols product. And also, you don't need to write down the anti-Markov-Nichols product in exam or midterms. Okay, you just need to write down the major product. Okay, mechanism. So it's a three-step mechanism. It's different from the HX addition. But the first step of the hydration is similar to the first step of the HX addition, which is the alkene add into an H. Okay, so the alkene has a pair of electrons go to a proton. And following Markov-Nichols rule, the proton will add into the carbon with more protons, right? You generate a very stable carbocation. And the carbocation is electron deficient. And the water can now add into, water has long pairs, right? Adding to the carbocation to generate a positive ion. And the third step, in the HX addition, this second step is X minus add here, right? But it's water add. So now the third step, which is the last step, another water molecule need to remove the H from this ion to generate the alcohol product. And now you have an H remaining, right? H is recovered. So that's why we call it the H a catalyst, because the starting material becomes the product, but the H as catalyst never changed. In the beginning, it's an H. In the middle, it participated in the reaction, but at the end of the reaction, the H remains an H. Okay, so the reason why the reaction needs an acid catalyst is because water itself does not ionize to produce enough proton to start. Okay, so again, by comparison, in the HX addition, the HX ionized very quickly to give a proton, but the water is very slow because it has a higher pKa. It's not that acidic, so you need to add an acid, strong acid, like a strong proton to initiate the reaction. All right, and the difference, and another difference between HX is that the water is usually used as the solvent amount. Okay, so the water's quantity is really abundant during the hydration reaction. And the third reaction, which is different from the HX addition, is that you need a deprotonation step at the end to recover the proton and get the alcohol product. Okay, so this is the reaction coordinate diagram of the hydration reaction. Okay, so so it has 3 steps now instead of the 2 steps for the HX addition. So in the HX addition, the first 2 steps looks alike, right? Because it also generates a carbocation. It's very unstable, so the second activation energy is really small because the instability of the carbocation really reactive to react with nucleophiles to generate the product. So in the HX addition product, so this should be the HX addition product, which I already have the X here. Okay, but in the hydration, it's more complicated because it has a third step, which actually needs to remove one H from this ion to give the alcohol product and regenerate the catalytic amount of strong proton to, and the proton will enter another reaction with the alkene to go through this again. Okay, but the first part, the majority of the mechanism is similar to HX addition. And the first step is H adding to alkene to generate unstable carbocation through a transition state here. And the rate determining step, do you know what's the rate determining step in this reaction? Do you still remember how to figure out what's the rate determining step of a reaction coordinate diagram? So you need to first find out the highest energy transition state. So we have 3 transition states here, this, and this. So the highest energy transition state is here, right? Then we need to figure out where is the highest energy transition state located. Where is TS1 located? It's located from here to here, right? So this step from the alkene to a carbocation is the rate determining step of this reaction. And that also explain the Markov-Nikolson rule, right? Because the active energy of the transition state, the one, actually determines the rate of the reaction. So, and the more stable carbocation indicate a more stable carbocationic transition state, and in this case, a Markov-Nikolson transition state, and to give this one. That's on internet is unstable. All right, so a similar acid catalyte addition of alcohol can also occur when the reaction is conducted in the alcohol as solvent instead of water. So instead of the abundant water nucleophiles, now what if you have abundant alcohol nucleophiles? So what's going to happen? Okay, so the net result is that an ether will be formed in a Markov-Nikolson pathway. So which the proton will add into this carbon, and the nucleophile OCH3 will add into here. So let me draw the mechanism, and you probably need to take out your pen and draw with me. All right. I mean, it's 2 weeks from midterm, so you need to practice now. All right, let's see. All right, so you have a alkene. And so you have a strong acid, which is a proton. Or you can draw the sulfuric acid structure here. Right? So the first step is the alkene will attack the proton. And then you can draw like this. So you will generate a carbocation, right? Positive. Now this becomes a CH3 because the proton adds into this carbon. So this proton adds into this carbon. Okay, then you have an electron deficient electrophile, right? So what's the nucleophile? The methanol. All right, so you have a methanol here. And the lone pair. Now the lone pair will attack the carbocation here. So what do you generate? You have H3, C, H, CH3. Remember, there is still a proton on the oxygen, okay? So do I miss anything? Yes, I missed a proton. Oh, no, I missed the positive charge. You need to be aware of that. You need to keep the charge and the valencies together, like equal with these two. You have a positive charge at the end. You should have another positive charge. Okay, then like the process of hydration, and we need to remove this proton. Okay, and the way we remove it is we remove it with another molecule of methanol. So lone pair attack here and goes back to oxygen. So you have your product. And then you have a protonated methanol. So, and this protonated methanol can be viewed as a proton plus a methanol. So this molecule can act as an electrophile to enter another reaction with the alkenes. So the alkenes will then react with this proton and you go through this ether formation. All right. So this is how we draw a mechanism for this addition of alcohol. Let's go back here. Remember to practice on drawing those curved arrows. So the product of the addition of alcohol is ether. Then we need to talk about the stereochemistry of the hydration reactions. Okay, so hydration in general can generate a sterol center on the alkene starting material, and the resulting chiral alcohol as the product. Okay, so but the addition of HOH or the ether is non-stereoselective. Okay, this is similar as the HX, right? So if you add the hydrogen bromide, it's non-stereoselective because the intermediate is a carbocation, which is a flat, right? And because it is flat, the nucleophile can attack from the top face or the bottom face, okay? So in this case, so imagine you generate a carbocation here, all right? And then the OH can attack from the above side or the bottom side. So from the above side, it generates S-butanol, and from the bottom side, it will generate this one, which is R-butanol, all right? And just as I draw it here, so you have a carbocation. And if you attack from the top, you can have the S. If you attack from the bottom, you can have the R-butanol. Okay, it's 50-50. And there's a mirror between them because they are enantiomers. All right, so this is exactly like the HX addition. You generate a carbocation, then the next addition step, the nucleophile, like the X, adding to the carbocation in a non-stereoselective way. Okay, then another thing about this is that, a similarity between the hydration and the HX addition is that because you generate a carbocation, right? And the carbocation, as we learned in the first period of this class, lecture, is that it can rearrange, okay? So as I said, because of the formation of carbocations, and there is rearranged product. So like here, so if you add into proton here, generate a carbocation, and this is the normal Markov-Nikov hydration product, all right? OH is bonded here. But if you do a carbocation rearrange to generate a more stable carbocation, the green H will migrate into the middle one, and the more stable tertiary carbocation generated, all right? And then the water will attack the tertiary carbocation and remove a proton, will give this rearranged hydration product. All right, just like the HX addition, if this appears in exam or test, you need to write down both products. One is Markov-Nikov, the other one is rearranged hydration product. All right, so because of this rearrangement issue of this carbocation, the reaction is only so that this hydration reaction is only good for the synthesis of simple alcohol. So those alcohols that from carbocations that do not rearrange, like the react with ethylene to give ethyl alcohol. All right. So this is not really a good laboratory level preparation of alcohol because due to this carbocation rearrangement issue. But the community, the synthesis community has actually come out of some pretty good way to synthesize those alcohols selectively. And in these cases that the rearrangement is no longer an issue. So one of these reactions is called oxymercuration and demercuration reactions. So why there is a combination of this oxy and the D process is that this process is actually consists of two separate reactions. Okay, the first one is what we call oxymercuration, and followed by a second reaction called demercuration. And this overall process can turn the alkene into alcohol, and the net process can be viewed as a hydrogen reaction, right? You add the HOH into the alkene, right, to give alcohol. And this is what selectivity here? Is this Markov-Nikov or anti-Markov-Nikov? So this is Markov-Nikov addition product. Okay, and as you can see, this starting material just look like this. It is exactly this. So you can see if we would use the acid catalyzed hydration reaction, we will have a rearranged product, which really complicated the reaction. Okay, but for the same starting material, if we use oxymercuration demercuration sequence, we don't have the rearranged product here. Okay, we have a very clean Markov-Nikov addition product. All right, so is this one. So we have one side, one hydrogen, the other side, no hydrogen. The reaction selectively gives the Markov-Nikov product with hydrogen added here and OH added to the more crowded carbon. Okay, so why is this sequence different from the hydration? And what's the role of the mercury? So first, I'm going to introduce you to the structures of this very important mercury species. Okay, so oxymercuration usually uses mercury 2 salts, like the mercury acetate. So OAC is actually this kind of structure with CH3. It's a carboxylic acid anion bonded to mercury, all right? And each carboxylic acid anion is counted as -1. So -1, -1, the mercury is 2+. All right, so the mercury acid can actually dissociate into this, like kick off one of the acetate anion, like here, and generate some kind of very electrophilic mercury species here. So the mercury has now a plus charge and the anion has a minus charge. So this bond breaks to give a very electrophilic positive mercury species. Okay, and then as we know, the alkenes are electrophiles, are nucleophiles because it has electron density, right? And this is electrophilic. So these two will react. So these two react in a way that the electron of the alkenes will go to this positive mercury atom. At the same time, a bond will form between the mercury and this crowded carbon. Okay, so the mercury shares the positive charge with this carbon. So this is 2 arrows. So if it's only 1 arrow, this will be a full carbocation, right? But in here, the mercury gives some electrons to this carbon. So the actual intermediate looks like this. Okay, there is some bonding between the tertiary carbon, tertiary carbon with the mercury. So this is what we call the mercurinian ion. It's like a brominium ion with unsymmetric alkene, right? So if you imagine this is a bromide, so the bromide has some interaction with here. This has some partially positive charge. Okay, so these two are the wrong intermediates for the unsymmetric alkenes, or in mercury case, the wrong species for the mercurinian ion. Okay, so it will not form a bond. It's only a partial bond, shares a little bit electrons with this one. It also will not generate this one because this is much unstable than this one because the positive charge, partial positive charge wants to stay on the more substituted carbon. Okay, so this one for the unsymmetric alkenes is correct, like this. Okay, this bond is partially positive. Okay, after we generate this mercurinian ion, now the nucleophile will attack because this has partially positive, right? So the abundant water will attack from here in the backside of this to generate a CO bond. And just like the hydration catalyzed by acid, the final step is the removal of 1 proton from this ion to give this OH. So, so this is much like the brominian ion, right? So this product is trans because the OH will attack on the backside of the this bond to break here, right? So the OH and the mercury on the different side of the ring, different side of the alkene, right? So step 1 plus step 2 is the oxymercuration as anti-addition, all right? But the bad thing about the oxymercuration and the demercuration process is that the third step is messy. What does that mean? So you have an anti-addition oxymercuration product, which the OH is on the different side of the mercury, okay? Then The demercuration usually use sodium borohydride, so which is a hydride source as a reductant. Okay, you will learn more about this in advanced organic chemistry course. So the net result is the mercury is replaced by H. Okay, the mercury becomes H. See, here. If you use the sodium borodeuterium, like the H with like D, okay, NABD form, then the mercury will be replaced by the D. All right, but the bad thing about this reaction is that the mechanism is not well understood, and the net result is that it will mess up the stereochemistry of this carbon. Okay, so at the beginning, the mercury on the on the opposite side of the OH, but at the end, it's all messed up. Now the mercury, now the hydrogen can be on the same side of the OH after it replaces the mercury. So we really don't understand the demercuration mechanism that well, but I would just ask you to memorize that the demercuration reaction is not a stereoselective reaction. Okay, although the oxymercuration generates a perfectly anti-addition product, the demercuration messed that up. All right, and the net result is that from an alkene, you do the oxymercuration demercuration sequence, you get the hydration product, but not stereoselectively. Okay, then the H added can be on the same side of OH and be on the other side of the OH. Okay, so this may not be may not be important here because there is another H here. Okay, but let's say if you use NABD form to replace the mercury, then it makes a difference, right? Because the D can be on the same side of the OH, on a different side of the OH. And another substituent here is an H. You have H and the D. And the D is can be cis or trans to the OH. Okay, so just to memorize that, the first step, oxymercuration, perfectly anti-addition. The second step, mess that up. So overall, the oxymercuration demercuration process, it's the non-stereoselective Markov-Nikov addition of water. All right, so again, if we can use water as solvent, as the abundant nucleophile to do the hydrogen reaction, we should be able to use the let's say alcohol as the abundant solvent or nucleophile to do the ether formation, right? Just like previously we talked about the acid catalyzed addition of the alcohol. Okay, so based on the mechanism of the oxymercuration and demercuration reaction, can you figure out what's the product of this reaction here? So take out your pen again. Let's practice on this together, all right? So what do we have here? So we have an alkene. Right? And as we say, the mercury diacetate can dissociate to a mercury plus acidic anion, right? And a mercury plus, as we know, is a very good electrophile. And the alkene can attack. Oh, too bad. The alkene can attack the mercury. And remember, the mercury will share some of its positive charge with this carbon, okay? Because this carbon is more substituted, but it's not like a string membrane, but just a little bit of sharing, all right? And also, let's assume the mercury is attacked from the bottom side, okay? So the mercury share a little electrons here. So what we have? We have a mercury that have a positive charge, partial positive charge here, partial positive charge here. Okay, then the OAC is left. If OAC is not left, sorry, OAC is here. Okay, then what do we have here? So we have our nucleophile coming up. Okay, the nucleophile is here, which has a nucleophile as a lone pair. Okay, it will attack at this carbon, but the attack will be on the opposite side of the mercury. Okay, as we draw the mercury here is in the back of this paper, so the OH will attack in the above. Okay, from the top. Okay, that makes the product will look like, so because OH attacked from the above, so the acyl group is in the bottom now. So the OH here has positive charge, all right? And the mercury, because the first oxymercuration is perfectly anti-addition, right? So the mercury will be on the back side. Right. So after this this addition of nucleophile, then what we have is that we'll have another molecule of the, just like the hydration reaction, we have another molecule of the alcohol deprotonate here. Then we have the product of the first step, the oxymercuration. But unlike hydration, we have alcohol linked to it. All right, then we have a second demercuration reaction. And the mechanism is not well understood. So as we say, this is anti, right? But as we said in the third step, what happened? The third step messed up that stereocenter, okay? So as a result, the anti-stereocenter is messed up by the reduction reactions using sodium borohydride. So although the first two steps are perfect anti-additions, in this step, it can be up or down. So sometimes we just draw this this type of waved bond to show that the H can be above the plane or below the plane. All right, but as a result, as a net result, the oxymercuration demercuration reaction using this sequence generates a product which is it's a Markov-Nikov selectivity with the CO bond formed as more crowded carbon here, and the H has a less crowded here. And this structure, because another substituent at this carbon is also H, right? So it doesn't matter this H is up or down. So you can simplify this structure as this. Okay. So if you give me this structure, you are 100% correct. So that's for this problem. So now we learned that the oxymercuration and the demercuration reaction. Okay, now let's take some time to summarize all these different mechanisms of the addition reaction. All right. So if you have a dihydrogen addition, which X is a bromide, or you have an oxymercuration reaction with the electron as mercury, so you will generate with this unsymmetric alkene, you will generate like a mercurinium ion or brominium ion that resembles tertiary carbocation, but it's not tertiary carbocation. Okay, the X, the bromide or the mercury shares some of its electrons with this carbon. So, and because of this sharing, the nucleophile can only attack from the opposite side as the substitution here. So the net result is that the addition is empty. Okay, so if you have a Br, then the 2Br will be on the opposite side. So if you have a mercury hydration, if this is OH, this is mercury, and the OH will be here, and the mercury will be here. It's empty. But for the Br, that's already the product, right? But for the mercury here, you need to remove the mercury, but the removal of the mercury messed up the stereochemistry. So it will not be, the overall process will not be empty. It's not stereoselective. But the first oxymercuration step to generate the mercury intermediate here is anti-selective. Okay, and because this is not exactly carbocation, it's stabilized by the mercury or by the bromide. So it's relatively more stable and does not rearrange. Okay, so the oxymercuration demercuration reaction is not stereoselective overall, but it doesn't give any carbocation rearrangement because it's not a classic carbocation. It's stabilized by the mercury in the intermediate. But for any of the reactions of the electrophilic additions that starts with addition to a proton, so because the proton cannot stabilize the carbocation, so the non-carbocation is the full carbocation. It's flat. And the next nucleophilic addition of the nucleophile can happen at both sides. And so it's not stereoselective, all right? So it will give two products, like the anti and the syn. And the second problem of starting with a proton is that it will rearrange because the carbocation now is complete. It cannot be stabilized by the proton. So that means that carbocation is a full carbocation that can rearrange. It can become a more stable carbocation. So as I write here, will rearrange if possible. Okay, so that's the general difference in mechanism between addition of one kind, which starts with the addition to bromide, chloride, mercury, and its difference between the addition to the proton to start the reaction. Okay, so you need to be crystal clear about difference in different mechanisms of different electrophilic addition reactions. All right. So all we talked about the hydration catalyzed by acid and these hydration catalyzed mediated by the mercury, the oxymercuration, demercuration reactions. So they are Markov-Nikov addition. All right. And what we have here is called a new reaction called a hydroboration oxidation. So it is also a two-step reaction, and its selectivity is different from the hydration and the mercury reactions. I will talk about this later. But as there is a hyphen in between, so this is also a two-step reaction. The first reaction is called hydroboration, and the second reaction is called oxidation. So in the first reaction, it's a hydroboration. So you can view this as a separate addition of H and the B. All right, so B adds to here, H adds to here. So hydroboration, okay? And then the second step is the addition of this carbon boron bond, which gives alcohol. So the net result is the hydration of alkenes. All right. So for the hydroboration reactions, the intermediate is here, as we call the trialkyl borane. And it's from the triple addition of BH3. So one H adding to one alkene. Okay, then 3H adding to 3 alkenes to generate this one. Okay, for the oxidation, each of this carbon boron bond is oxidized to a carbon oxygen bond, which gives the alcohol product. So the overall process is a hydration reaction. So, as I told you, the selectivity of this hydroboration oxidation sequence is different from the normal hydration reactions. So for the acid catalyzed hydration, because you generate a carbocation at the more stable condition, position, you have a Markov-Nikov addition of water. But if you go through a hydroboration oxidation sequence of this unsymmetrical double bond, you get an anti-Markovnikov addition. So the H now goes to the H that goes to the carbon with the less H, and the oxygen goes to the less crowded carbon. That is totally different from the normal Markovnikov addition of water, right? Okay, so the mechanism of hydroboration oxidation enabled this type of anti-Markovnikov addition selectivity. Okay, why? So I'm going to go through this with you, right? So the step one of the hydroboration oxidation reaction is that the BH, this bond, adding to this here, right? So the H goes to here, the B goes to here. So the BH bond is broken. And imagine if the remaining two BH bonds do the same thing with this, I will do a second one, a third one, okay? So why BH3 can do this kind of reaction is that the BH3 is very, very strong Lewis acid, okay? It has 6 electrons in outer shell, okay? Each pair of electrons comes from a BH bond, okay? And it is very electron deficient because the boron does not have a field octet, like here. So it only has 6 electrons on the boron, right? 2, 4, 6. So it lacks electrons. It needs electrons to field octet. So it lacks electrons, so it is electrophilic. And the electron pairs, such as the oxygen atoms in the ether, coordinated to the electron deficient boron. So that's why, so the boron itself can form a dimer. In the dimer, the H2 electron can share between these two boron. And these dimers can react with solvent like THF, like a tetrahydrofuran. So the O has a long pair, can donate into the boron to form this borane THF complex. So nowadays in lab, if you want to do the hydroboration oxidation reactions, you can directly buy those bottles of borane THF complex. So it's basically borane in THF solvent, and inside they are bonded, like the OH, the O of the tetrahydrofuran and the BH3 are complex each with each other. Okay, so the mechanism of this addition is considered via a full-centered transition state. Okay, no intermediates, it's concerted. So once, because the boron is electron deficient, the alkene will donate a pair of electrons to boron, and this bond will break spontaneously or at the simultaneously and form a bond with this carbon. So 2 arrows at one time, 4-member ring transition state to form this 2 new bonds. Okay, and because this is concerted, as this CB bond formed, this CH bond formed on the same side, so the net result is that the BH addition is a syn addition. It's a stereoselective addition of H and the BH2 on the same side of the alkene. Okay, so but now we know that it goes through a 4-member transition state. What if there is an unsymmetric alkene? Let's see what gives that anti-Markovnikov selectivities. So for these BH bond to add into the alkene, like the methylcyclopentene, if it goes through this transition state, so the small h, right, much smaller than B, will be on the same side of the methyl, right? Because if the B, the boron is on the same side of the methyl, 2 big groups are on the same side, okay? This is really crowded, but this is not. So because this concerted mechanism, and because the methyl needs to be far away from the borane to avoid any interaction or to avoid the crowded situation, so the B will end up on the less crowded side. Okay, and remember the B will eventually become OH, and so the OH will be here, and the H in the Markovnikov addition, the H will be on the carbon with more H, right? But in here, because this transition state, the H now will be on the side with the less H. Okay, that's anti-Markovnikov selectivity. All right, so let's see here. So if you have an unsymmetric alkenes, so the BH addition will have the B on the less crowded, the H will be on the crowded side now. All right, and because it is the syn addition, so the new H will be on the same side with the boron. That means the methyl, which is originally here, will be on the opposite side of the B and the H on the same side of the B, same, and anti-Markov-Nikov addition. And if this kind of syn and anti-Markov-Nikov addition happens 3 times, you can have a tri-alkyl borane. Okay, and if you think about all these reactions and think about this transition state, it is easy to understand that if the borane is very crowded, the selectivity must be higher, right? Because if the borane is big, very big, it will try to avoid the methyl very much. Okay, so that's why of all these 3 steps of hydroboration, the third step, which has the very big borane as the starting material, will be the most regioselective. And a lot of organic chemists are very smart. So they think, so if the third step is very, very regioselective, okay, how about we just use borane that is very big? For example, if we directly use a dialkyl borane, like 9BBN, so this is a borane which is sterically demanding. It has a very big ring structure, a bridge ring structures, very big. So that means this interaction will be very, very unfavored because this big ring structure will clash with the methyl, which is unfavored. Okay, so 9BBN is a frequently used hydroboration reagent in lab because it gives a very high regioselectivity. So the borane will be on the less crowded side very eagerly. Okay. So the second step. So after these trialkyl borane is generated, how does it become the alcohol? Okay. So the first step is that we normally use a basic condition with hydrogen peroxide, which will generate a peroxide anion. And the peroxide anion, because this boron is neutral and it has an unfilled octet, it's electrophilic. So it will react with this nucleophilic hydrogen peroxide anion. Okay, it will form these negative boron, which has a filled octet, negative charge. All right. Then the next 1Q alkyl migration step is really important. You guys need to focus on this. So this bond, instead of bonding to the boron, will migrate to the oxygen here and kick off the OH. Okay, and during the migration, it will become this structure. All right. So this CB bond broken, this CB bond broken. The C now bonded to O. Okay, the O is still bonded to boron. The OH is gone. All right. And during this step, the carbon stereochemistry, as this is pointing back, remained. All right. So this is dashed bond to B. This is dashed bond to O. Okay. During the oxidation step, the stereochemistry of this carbon does not change. Okay. So you guys can practice the next mechanism for these another oxidation of these two carbon boron bond. So the net result is that boron is now bonded to 3O and the carbon bonded to 3O's, bonded to 1O. And at the final step, the OH will attack the boron and to become a negative boron, and this will leave. This bond will break to form the alcohol. And because during the hydroboration during the oxidation step, the stereochemistry of this bond is remained. So the B usually be here. The B is pointing back. Now the product, the OH, is pointing back too. So, and due to the remaining of the stereochemistry, so this trans relationship remains. Okay. So from here, you have this pointing back. Now you have the OH pointing back. All right. And I think we're running out of time, but so just a little touch on this. So it's we will go back to and talk detail about this. So because the syn addition of the hydroboration and the retention of stereochemistry, so the overall process is the syn addition and the anti-Markov-Nikov regioselectivity of the overall hydroboration oxidation sequence, which gives the anti-Markov-Nikov hydration product. All right. So I think time is up. So we will talk in detail, reinforce your understanding of this on Friday, and we will summarize these hydration chemistry. We will go to the final part of the alkene, which is oxidation and the reduction, and we will definitely finish the oxidation reduction part of the chapter 5 to 6. and we will start chapter 7 next time.